In this video, we are going to talk about inclined plane problems and how to do them. So the first thing that you want to do is sketch the situation, and it's really important to draw both the inclined plane and the object on the inclined plane. Then you want to draw the force of gravity going straight down off of your object. So I'm going to just draw this along with you so that you can see what I'm saying. So we have our inclined plane, and you can just sketch it. It doesn't have to be perfect. You have your object on the inclined plane, and then you draw your force of gravity acting straight down, and then you label it. Then you're going to rotate your paper so that this right here looks horizontal to you. So you go till that looks horizontal, and then you're going to draw an x-axis parallel to the surface and through the center of mass. So I might draw my x-axis like this, parallel to the surface, and then you draw your y-axis perpendicular to the surface. So what we're doing is we're rotating our x and y directions. We've talked about how you can establish what the positive and negative directions are. Well, you can even rotate them, and this will make our math a whole lot easier by rotating the axes so that the incline is parallel to the x-axis. And a main reason here is that if this box were to slide down the incline, then it's moving only in the x direction. It's not moving in the x and the y direction. So it's going to make things a lot easier on us. Then we need to select positive direction. So I usually choose up or to the right and up as positive. But like I said, you can choose that the way that however you want. Then you can draw your other forces. So this one might have normal force, which would be perpendicular to the surface. So that goes right along the y-axis. And then you would split any of your vectors into components so that need it to be. So for instance, gravity is not acting just in the y or just in the x. It's acting both in the x and the y. So I could draw gravity's components like this. I'm going to split it into components and make it a right triangle. Now it's important to show that this force of gravity in the x direction, that's, oh goodness, in the y direction, that is along the y-axis, and then the force of gravity in the x direction is parallel to the x direction there. And then you write net force equations for the x and y directions. You're going to write one for the x direction and one for the y direction. And then you solve for unknowns just like you would any two-dimensional motion problem. So let's give a problem a try. We're going to do a couple of them. We're going to start with an inclined plane. And this inclined plane is going to have a box on it. And let's say that this is 30 degrees. So we're going to start off with frictionless. And we want to find the acceleration. We could give the mass of the box 10 kilograms. So we're going to follow our steps. We're first going to draw we sketch the situation. Now we can draw the force of gravity on the box straight down. And then we can draw our axes. Our x-axis is going to be parallel to the incline, and our y-axis is going to be perpendicular to the incline. And then we'll draw our other forces. We have a normal force acting perpendicular to the surface. And then we're going to split gravity into components. So I have, this is Fgy, and this is Fgx. Great. I'm going to zoom in a little bit to make sure that you can see this well. And now we need to find so we've got our situation drawn. We need to find the components of our force of gravity so that we know what to plug into the equation. You can do this now, or you could write your net force equations first. It doesn't really matter, but you are going to have to split force of gravity into components. Now something that's going to be helpful for you for splitting things into components is to figure out what these angles are in this triangle. So you can see here that this is a 30-degree angle. So if I had a triangle right here, if I made a little right triangle with this force of gravity arrow and the 30 degrees, we would know that this one up here would be 60 degrees. And since this angle is, okay, so this one is 60, which means that this one right here is 60. Those are the same. And then this is a right angle right here between the y-axis and the x-axis, so that means that this angle right here is 30 degrees. So if you always draw your gravity components so that your y component is opposite of your normal force, this top angle right here will be the same as this angle of the incline. That's a good thing to study and to know. All right, so now I'm gonna split my gravity into components. So I have, I'm just gonna leave this in symbols for right now. So I have F, G, Y is what we're going to solve for first. And this is a 90-degree triangle. So we can use sine, cosine, and tangent to figure things out. And the force of gravity in the y direction is going to be equal to the force of gravity times the cosine of theta. So I'm going to expand that a little bit. Force of gravity is m times g times cosine theta. Then we have force of gravity in the x direction, which is equal to force of gravity times the sine of theta. So that is mg sine theta. All right, now let's write some net force equations. We have a net force equation in the x direction and a net force equation in the y direction. Now we're looking for the acceleration, and since the acceleration is in the x direction, really the only equation we need is the net force equation for the x direction. So even though this instructions say draw one for the x and draw one for the y, you may not always need them both depending on what you're solving for. In this case, I'm not solving for normal force or anything in the y direction, so I don't actually need to write a net force equation in the y direction. So we have net force in the x direction is equal to the force of gravity in the x direction plus nothing, right? Because there's no resistive force, it is frictionless. So there's nothing else there. All right, so our net force in the x direction is our, we're gonna follow Newton's second law, and we're going to replace, since net force is equal to mass times acceleration, we're gonna replace net force with mass times acceleration. And that is equal to my force of gravity in the x direction, which is mg cosine theta, or sine theta, excuse me. Now, notice what happens. Now, this is one of the reasons we want to keep our equations in variables until the very end, because sometimes things cancel. Mass cancels. So acceleration is equal to g times the sine of theta. So I can put any different object on here with any mass. As long as it's frictionless, it will all accelerate at the same rate. And that should make sense to you from the free fall discussions that we've had and why objects accelerate at the same rate in free fall on Earth. The inclined plane is basically just slowing down that acceleration by counteracting some of the gravitational force with a normal force, but it still works in the same way. So this is an important thing to know how to derive and to understand how to use. So we could find the acceleration here by doing g sine theta, so 9.8 meters per second squared, times sine of 30 degrees. And we can type that in on our calculator if you need to, or maybe you have your trig functions memorized enough to know that sine 30 is 1/2, or maybe you just didn't quite remember them, but then you type it in on your calculator and say, ah, I should have known that. So there we go, 4.9 meters per second squared. All right, next question. Now let's try to do the same situation, but this time we're going to say that the acceleration is 0. We'll say the mass is still 10, Although in this part it didn't matter, right? So it didn't matter up here. But now the mass is 10, acceleration is 0, so that means that our forces are balanced. And we want to find the frictional force and the normal force. I'm going to draw the diagram again just because it'll help you to see it drawn multiple times to help you remember how to do it. So we have our diagram, we have our 30 degrees, we have our object, we draw our dot, then we draw our force of gravity. Sorry, I want that there. Force of gravity is down. I'm gonna make it super long. I don't know why. And then we are going to rotate our paper so that the plane looks horizontal to us. This is helpful when you're drawing your axes. And then draw your components. This will also be helpful when you're drawing your components. It'll help you not make mistakes to keep it rotated while you're doing this part. Because you want to make sure that when you turn your force of gravity into a 90-degree angle, or a 90-degree triangle, the right angle is right here. It's between the force of gravity and the y. Oops, I wrote force of gravity and the x. Or y twice. Force of gravity and the x, it's between those two. A common thing that I see is drawing the x component like this way, so that the 90-degree angle is here, which is not correct. So make sure you're careful with that. Okay, and then we draw our normal force straight up. Rotating your paper will also help you draw your normal force perpendicular to the surface. So the normal force is there. And as you're drawing this and trying to figure out how to scale it, usually if there's no like forces pushing down on the object or pulling up on the object, the force of gravity in the y direction is going to be equal in magnitude to the normal force. And then since this one has an acceleration of 0, I know that I have a frictional force, and that frictional force is acting up the incline. And if my forces are all balanced, his acceleration is 0, then these two should have the same magnitude, the x component of gravity and the force of friction. So there's my diagram. Now I'm going to write my net force equations. So I'll write a net force equation for the x direction, which is force of gravity in the x plus force of friction. And I did not establish my positive directions. And then I write my force or net force equation in the y direction equals force of gravity in the y direction plus the normal force. I also need to find my components of gravity. So I'm using the same process that I used up here, where I have force of gravity in the y direction equals Fg cosine theta. So mg cosine theta. And then force of gravity in the x direction equals Fg sine theta, which is mass times gravitational field strength times sine of theta. All right. So now I'm going to apply that to my net force equations. Now I know that the net force is 0 because acceleration is 0, is equal to my force of gravity in the x direction, which is it's acting in the positive direction, so that's going to be mg sine theta plus force of friction. And then I can solve for force of friction by subtracting that to the other side, and then I'm going to switch them. So I get force of friction is equal to negative mg sine theta. Plug in some numbers here. We get negative 10 kilograms times 9.8 newtons per kilogram. You may be saying, wait, isn't the 9.8 negative? And yes, it does act down, but I've already taken into account well, my positive direction is actually down the incline. So in this case, my force of gravity is acting in the positive direction. So that needs to be a positive number. And then sine of 30 degrees. So we get force of friction is equal to 10 times 9.8, you see my calculator, yes, times sine of 30. Make sure you're in degrees when you do this, because if you're in radians, you won't get the right answer. And once again, I could have done that in my head. So we have negative 49 newtons. And then always double check yourself on the sign. The force of friction is in fact acting in the negative x direction, so it should be negative. Then we go over to the y direction. In the y direction, the net force is also 0 because the block is not accelerating in the y direction. Force of gravity in the y direction is mg cosine theta. And then we add the normal force. And then we're going to solve for normal force. So we get normal force is equal to negative mg cosine theta. And then we'll plug in numbers. So negative mass is 10 kilograms. Now in this case, this value, mg cosine theta, that is a negative value because it's going in the negative direction. So I have to put in a negative sign somewhere. I'm going to put it right here. It doesn't really matter where you put it. Some people actually calculate this first, like up here, and then have a negative value just to plug in. I like to keep it in variables till the very end because, oops, some things will cancel out like they did in the first problem. So cosine 30, and we get, so this should be a positive, which it is because I've got two negatives. So 10 times 9.8 times the cosine of 30 gives us 84.8, we'll just round to 85. 85 newtons, and that should be positive. We can double check ourselves because it's acting in the positive y direction. So there is another example. All right, we're going to do one more. And this one is going to be a little bit different. So we're going to have our inclined plane. We're going to have a box on the inclined plane. Let's make this 35 degrees. And we're going to say the mass of the box is, we'll just keep it at 10 kilograms. Let's say the coefficient of friction is 0.2, and that's kinetic friction. And then we will say that we need to find the acceleration. So in this case, we are going to follow the same steps that we followed before. So the first thing we do is sketch the situation. We're going to draw a force of gravity arrow down, rotate our paper so that we have it, this looks horizontal to you. Then you draw your x-axis and then your y-axis. So x-axis parallel to the inclined plane, y-axis perpendicular, and that's positive y. And then we draw our other forces. So we have normal force, and we have frictional force. Frictional force is going to be opposite of motion, so let's say that it's sliding down, because if it was sliding up, then you would have frictional force going this way. So it's sliding down, so we're going to put a frictional force this way, and I'm going to guess that frictional force is less than force of gravity, but I don't really know, so I'm just going to draw it a little smaller than the force of gravity in the x direction, but I could be wrong. Okay, so force of gravity in the x, force of gravity in the y, and this right here is 35 degrees. So there I have my diagram drawn. And some things you should notice, the force of gravity in the y direction and the normal force are equal in magnitude. And then the force of friction acting up and the force of gravity in the x direction, those should be unequal because it's accelerating in that direction. So now we're going to we need to split gravity into components and write net force equations. So let's just split gravity into components here. So force of gravity equals force of gravity in the y direction is equal to the force of gravity times the cosine of theta. Force of gravity in the x direction is equal to force of gravity times the sine of theta. And then we can say this is mg cosine theta and mg sine theta. Okay, I'm gonna go ahead and solve, well, we'll just do force. Okay, sorry. So now we write our net force equations. So this should look very familiar, right? Force of gravity in the x direction is equal to net force in the x direction is equal to force of gravity in the x direction plus force of friction. And then sum of the forces in the y direction is equal to the normal force plus the force of gravity in the y direction. All right, now let's work with this one first because we're solving for acceleration. So this is what we're looking for, something in here. Now we know that the net force in the x direction is mass times acceleration. So mass times acceleration in the x direction is equal to my force of gravity in the x direction, which is mg sine theta. And then my frictional force, my equation for frictional force is mu kinetic times the normal force. Let's think about if we can solve for this. We know mass, acceleration is what we're looking for. We know mass, we know gravitational field strength, we know theta. We know mu, we don't know normal force. So what we're gonna have to do is use my y direction equation to determine what normal force is and then plug it in over here so that we can solve for acceleration. So let's go over to y direction. My net force in the y direction is 0. My normal force is what we're solving for. And this is gonna be just like we solved it before. So we'll put mg cosine theta here. Then we solve for normal force. That's equal to negative mg cosine theta. And then we plug in numbers. So we've got, I'm going to put my negative sign there just to show you a different way to do it. 10 kilograms times 9.8 newtons per kilogram. I know that this y component of gravity is a negative value because it's acting in the negative y, times the cosine of 35 degrees. So I get, lost my vector symbols, 98 times the cosine of 35. So I get a normal force of 80 newtons. Now I can plug that into here. So first I'm going to isolate my A. I get A equals mg sine theta plus mu times the normal force divided by mass. And now I'm going to plug in numbers. So acceleration equals, my mass is 10 kilograms. Gravitational field strength is 9.8 newtons per kilogram. Sine of 35 degrees plus mu, which is 0.2, times the normal force, which is 80 newtons, divided by 10 kilograms. All right, so we have 98 times the sine of 35, and then we add 0.2 times 80, and then we divide by 10. And we get 7.2 meters per second squared. That seems too big. Did I do something wrong? Oh. We forgot to make this negative. This is a negative value because it's acting in the negative direction. So let's try that again. Much better. We got 4.02 meters per second squared as the acceleration of the box. Let's think about a couple of things here. I did forget to make this a negative number. I was adding my vectors up here, so I have to insert a negative number for my force of friction. Another way to write this would have been to write the sum of the forces in the x direction equal force of gravity in the x direction minus force of friction. So you write it without the vector symbols on top, and then you would just plug in the positive number there. But since I wrote it with vector symbols and used the addition, I have to insert a negative number here. So that was my issue. Now in the end, I got a positive acceleration. So that tells me that this is speeding up. It's moving down the incline and it's speeding up. That's all.